Hi, it's Mr. Townsend here. Have you ever wondered how Newton or Einstein came up with their famous equations? Force equals mass times acceleration, and E equals mc squared? Well, in this video, we're going to learn how to derive an equation from experimental observation. We're going to do that by drawing a line graph and calculating the graph equation. For this exercise, we're going to say that we carried out an experiment where we dropped a balloon and we measured how far it traveled over different distances. Sorry, how long it took to travel different distances. When we drop a balloon, it very quickly reaches its terminal velocity. That's the maximum speed it can go. It does that because it has such a large friction that when we drop it through the air, the friction force is equal to the gravity force very quickly at a very low speed. So we drop the balloon, we start recording when it hits the start line. We have let's see what we do here. We drop a balloon, we start the recording when it falls past the start line, and then we stop it when it falls past, say, the 0.5 meter, the 1.0 meter, the 1.5, and go and on and on. From that, we're going to have a set of data that we can use to calculate the terminal velocity or the graph equation. And that's what we're going to focus on with the rest of the video, is how we go through and actually draw an accurate graph and calculate a graph equation. Okay, so the first thing we're going to do when we go and draw a graph is we're going to have to give it a title. In this case, the data that I've collected, I've given a heading for that or a title for that, the time of the balloon to fall. That's an appropriate title. I could use that, but I'm actually going to use a slightly different one. I'm just going to call the title what speed of falling balloon, because that is what we're going to calculate from this when we get this graph equation. So I need to select then the variable that goes along the bottom. That's usually the independent variable, or the variable that you've chosen the specific values for. But actually, when time is involved, time is actually the one we're going to put on the x-axis, because it just is more important than any other variable. It actually never impacted by any other variable. We say time is constant, so we always put time on the x-axis. So I'm going to go ahead and put time on the x-axis. Now, instead of just writing the name, I'm just going to replace it with the symbol. So I'm going to put t, little t, and in brackets, I'm going to put the unit. It's going to be measured in seconds. And then I look down my column here and I see my biggest number is 1.2. And if I count along the bottom, I've got 20 lines. So it doesn't go easily into 20. 20 doesn't go easily into 1.2. I'm not going to be able to break that up easily. So what I've decided to do is I'm going to go 0.1 for each line, but I'm only going to label every second one. So I'm going to label it 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4. Now notice I didn't use all of the available space here, but I've used a good proportion of it, so that's good. But better than that, I've chosen a very nice, easy step. So every one of these lines goes up in 0.1, and that's going to help me when I go to plot my points. Okay, so I'm now going to label the next axis, the y-axis, sorry, and that's obviously going to be our distance. It's going to be measured in meters. So I've got d brackets meters, and again, I'm going to choose a scale. But it so happens that I've got 20 boxes and I've got 2.5. So I can split 20 5 times. So if I divide 20 by 5, that gives me 4. So every 4 boxes is going to go up 0.5. Look, just trial this and see how you go. So I'm going to put 0 here. I'm going to go up 4 boxes, 0.5, then 1, 1.5. 2.0 and 2.5. So actually this scale's worked out really well. It's going to be a wee bit trickier to plot, but it doesn't really matter because I know exactly what the values are when I go to plot them for distance. So now I have to plot each individual point. So I'm going to go along to time. I'm going to go along to 3.1. Okay, on the time, on the x-axis, I'm going to go up. and then I'm going to plot at 0.5 and put a cross right at the point. Now I use a cross. A cross gives us a nice big mark to see, and where the two lines intersect on the cross is the exact point we're looking for. So it's accurate, but it's big and it's easy to see. So that's a lot better than a fine dot. So I'm going to go and actually plot the other points now. So 0.5, 1, and then I've got 0.72 and 1.5 and 0.95 and 2, and then the last one, it's 0.118. So I know that this line here is 0.11 and this line is 0.12. So I know that the next decimal point, if it's an 8, is going to be along an 1/8 way along this line here. So it's going to be closer to this line than it is to here, and it's going to be a bit further away from the center between those two lines. So I'm trying to actually think of a scale between each line so I can actually plot each point accurately, right? So this is an 1/8 across from this line to this one, and I've plotted that point. So now I've got all my points plotted. I want to draw a line of best fit. Now, line of best fit is a straight line drawn with a ruler that has the points equally weighted above and below the line at the top and the bottom. So here's my first attempt. There it is. Okay, in my first attempt, what I've done is I've started it at 0. Now I don't have to, because there's actually not a value given for 0. So if there isn't a value given for 0, you don't have to start the line at 0. Now notice when I did try and balance them, what happens is at the top, the 2 points are above the line, and at the bottom, the points are below the line. So it's not balanced, it's imbalanced. So I need to redraw this. So here I go again. I've redrawn a better line, but the problem is it doesn't go through 0. That's all right. There's usually a reason for why it doesn't go through 0. It's to do with an error that I might have made in the experiment that I might explain. Notice the blue line here, which is my better line of best fit, has the points a lot closer to the blue line, and they're equally spaced above and below as we go along the length of the line. So that's the line of the best fit, and that's the one we're going to go and calculate the gradient for, so we can work out the graph equation. Okay, so now what we're going to do is we're going to calculate the gradient. So in order to calculate the gradient, the first thing I'm going to do is I'm going to select a couple of points on the x-axis. Those 2 points are actually going to be at 0.2 and 1.1. They're going to be two values that are actually on a line, so it's going to be easier for me to draw a vertical line upwards. And they're going to be at least 2/3 along the length of the axes that I'm using. So 2/3, so I get a nice proportion of my graph. I use that when I'm going to calculate my gradient. So the first line I'm going to do is I'm going to draw a vertical line from 0.2 straight up. Then where I hit the line of best fit, I'm just going to draw a horizontal line, and I'm going to work out what that value is. I'm just going to write it on the side of the graph here. So here, the value for this line on the x-axis is 0.2, on the y-axis is 0.25, because it's halfway between 0.0 and 0.5. Now I'm going to choose to draw the line for the second point that I've thought about choosing, which is 1.1. Now these points that I'm choosing here, we have to be certain that they're not actually points that were plotted. They're not the plotted points, but they're just random points, a reasonable distance across the line of the graph, that are going to produce, I guess, a vertical and a horizontal line where it intersects. Now, so I've drawn my vertical line up of 1.0, and I draw it across from where it intersects. Now, it's not going to intersect perfectly on a line. That's what happens. And then after that, we're going to have to guess appropriately about where we think between 2.0 and 2.5 this horizontal line that we've drawn from this intersection is. And here I've had a reasonable guess, and I said it's 0.235. So we can calculate here now, since I know an initial time value and I know, I know a smaller time value and a larger time value, or a change in two time values. So I want to find, well, what is the change in the time between these 2 points that I've selected on my graph? And the change in the time is just the larger point subtract, the larger value subtract the smaller one. So the change in time is 1.1 minus 0.2. Now notice I wrote it 1.10 and 0.20, and that's because when I read this off the graph, it wasn't roughly 1.1, it was exactly 1.1.0. If it had been 1.1.5, it would have been halfway between these two lines. So I've put the extra decimal place to show the accuracy to which I read the graph. So the answer is going to also have these two decimal places here. Now I'm going to work out the change or the difference between these 2 points with the distance or the x-axis. You can see it's 2.35 and minus 0.25. And the answer, of course, I get here is 2.10 meters. So now I know the time, the change in the time, and the change in the distance for 2 points on the graph. And remember, we chose those 2 points by drawing these vertical and horizontal lines. I'm now going to calculate the gradient. Now you might remember from maths that the gradient is the rise over run, but here in science we're going to say that the gradient equals the change in x, which is the rise, over the change in y. Now in this case, m is the symbol we use for gradient. So m actually equals y, which is distance in this case. The y-axis has the value distance. So the gradient equals the change in distance over change in time. So I'm now going to substitute the change in distance, which is 2.1, and we're going to divide it by the change in time, which is 9.0. And then that will give us the gradient. So we calculate that, and the gradient is now 2.33 meters per second. Now, where did I get this unit from? Well, notice that at the top here, I'm dividing distance by time, so that's meters. Okay, so that's the unit, so is being divided by seconds. Now, because seconds is dividing into meters, we write it as -1, or per second. So this is meters per second. And that's how we work out what the units are. Now, you're not always expected to write down the units or work out what they are, but this is how we do it. Okay, let's go on to the next slide and look at, well, we now have a gradient. How do we actually write the graph equation? Okay, so we've worked out the gradient. Here it is. It's 2.33 meters per second. Remember, we don't have to have the unit. But remember, gradient, the mathematical symbol for gradient is m. So I'm just going to write it down as m equals 2.33 meters per second. Now, the graph equation always has the following form for a straight line graph, a linear graph. It's y value equals mx plus c. Now, y is the variable, which is on the y-axis, which is distance in this. M is the gradient, x is the variable on the x-axis, and c is the intercept. So if I wanted to write the graph equation here, instead of writing y, okay, so this equation here is just to help us, remind us how to draw it, I'm going to put in the variable that is on the y-axis, and that is d. And then instead of writing m, I'm going to put in the gradient. That is 2.33. Instead of putting x, remember that's the variable from the x-axis, I'm going to put in time. And if I need to put an intercept, and in this case there is one, so I'm going to put it in. It's not always needed, depending on what type of exercise you're doing. But here's the intercept, c, and I'm going to put that down here in my graph equation. So this is my graph equation. And this is usually the end product of what we want to get when we carry out these experiments is a graph equation. Now, you have to be certain when you draw your graph equation that you have substituted the generic y with the specific value that it is. That is d for distance. The generic x with the specific value that is on the x-axis, that's time, and make sure that you put the gradient in between. So let's just have one quick recap and then I'll let you go. Now look, if you found the work that I've done on this video useful, don't forget to like it and recommend it to others, because a lot of people have trouble with calculating these graph equations. And actually, if we practice them and we just make sure we do things properly, we can produce a graph equation that's correct, and we can use it to solve problems. So the type of problems we might solve is, so here's our graph equation that we just had. The distance equals 2.33 time plus 0.2. Now, what it actually means is the distance that something travels will be 2.33 times the time it took in seconds for it to travel. So if I was to ask something like, how far would a balloon fall after 20 seconds, I could go and replace 20 into where the t is here, and I could work out the distance it would travel. And the answer here is that it would travel 46.8 meters. Now, that's what makes a graph so useful. Sorry, not a graph. What makes the whole graphing exercises, but the graph equation so useful is it becomes a physics equation. I can now use it to solve real world problems. Now, most people don't want to know how far a balloon falls, but you might want to know how long it would take you to travel in an aeroplane from one airport to another, so that you could put the arrival times. Anyway, hopefully that's been useful. Look out for my future videos. Thanks a lot. See you later.